Before we start this chapter of rotational motion, it is important for us to recall what were all those parameters which we were using while solving questions of linear motion. So the basics were displacement, velocity, and acceleration. And then we dealt with mass, force, linear momentum, and kinetic energy. Now, in this particular chapter, rotational motion or angular motion, there is a corresponding term for each of these terms which we have discussed. For example, in linear motion, we talk about linear displacement. In angular motion, the term is angular displacement, and the symbol for that is theta. Speed or velocity, that is the linear speed, that's for the linear motion. For the angular motion, we have angular speed, the symbol is omega. For acceleration, the angular counterpart is angular acceleration, the symbol is alpha. For mass, see, this is the tricky point. Mass in linear motion is equivalent to a term called moment of inertia in angular motion. We are going to consider moment of inertia in much more detail, but for now, just remember the corresponding term for mass is moment of inertia in angular motion. Next off, we have force. So the corresponding term is called the torque. Linear momentum in linear motion, the corresponding term for that is angular motion, and the symbol is L. Now, finally, kinetic energy in linear motion. For the angular motion, we call it as rotational kinetic energy. So, during this entire chapter of rotational motion, we are going to consider various formulas which connect all these parameters. So, let us start. So, here you can see I have mentioned the definition of what is a rigid body. So, rigid body is a solid object that doesn't deform or change shape even when external forces are applied. So, rigid body is basically a solid. Now, on the other hand, the other objects which are not considered in this category are called fluid objects. By fluids, we either mean liquids or gases. So, this is the distinction. Rigid body is just a solid object. Now, what is the importance of this in this particular chapter? So, please read. It's mentioned motion of a rigid body depends on force and the point of application of force. So, let me play this video and let's analyze this concept. So you can see if we apply a force on the top, this object has a tendency to rotate. If you change the point of application of force, this is still rotating. Now, as we keep going closer to the center, now observe when the force acts at the center, it actually doesn't rotate, it moves in a straight line. So let's watch it together again. The force is at the topmost point, so it has a tendency to rotate. As you can see, we change the point of application force, it still rotates. So let's read this. It's mentioned motion of a rigid body depends on force and the point of application of force. So this is a video. Let me play this video. So this is an object on which we are going to apply different forces at different points. So let's go. So the first force, you can see it is acting on the topmost point, and now you can see the object is rotating. Now all we are doing is we just keep changing the point of applications of force, and you will see different types of motion of this object. But there will be one situation when the object doesn't rotate, like as you can see in this case. Let me play this one more time. So if the object is being pushed at the topmost point, it does rotate, as you can see. So if we keep changing the point of application of force, analyze the motion. Now there will be one particular point in this. If you push the object along that point, it does not rotate. It just goes in a straight line. So watch this. This is that situation when the object does not rotate, it is just going in a straight line. And now let us understand this in a little more detail. Case 1. The force applied is passing through the center of mass of the rigid isolated body. So have a look. Let's say this is a rod, for example, a rectangular rod, and this black dot represents the center of mass. Now, if the applied force is passing through the center of mass, this entire rod is just going to move straight ahead in a straight line. So what we can say here, if the force acts through the center of mass, there is only linear motion that is happening and there is no rotation effect. On the other hand, if the force does not act on the center of mass of the rigid body, now we'll have two subcases. Subcase number one, if the body is hinged. What do I mean by a hinged body? So consider this diagram. We have the same rectangular rod. This black dot is the center of mass, but consider this center of mass is also the hinge or the pivot. Now, what do I mean by this point? What is a hinge or what is a pivot? So, a hinge is a point about which the object is fixed, which means that particular point cannot move even though the entire object can rotate. but that particular point cannot move. So let me give you a simpler example. So have a look. This is a diagram of a door, and you might have seen these objects connected to the door. These are called the hinges. Now, it is the hinges which allow the door to rotate, and the door rotates about a line which is called the axis of rotation. So if you connect a straight line which connects all these hinges, so let's say if I draw a vertical line here, that will be the axis of rotation for the door. And that is why in the questions, whenever they say the body is hinged, which means it is fixed with respect to a particular point. So the body can rotate, but that particular point is not movable. So in this situation, if a force is acting on a hinged body, then the object is going to rotate, as you can see here. So as opposed to case one, where linear motion only was happening, in case of a hinged body, only rotation effect is taking place. So the object cannot move in a straight line, it cannot move ahead like what was happening in case 1, but here only rotation effect is taking place. On the other hand, in this, if I consider the sub case 2, when the body is not hinged, so the force is not acting on the center of mass, but the body is not fixed with respect to any point. So there is no hinge, no pivot point. So what is going to happen in this situation? So this is the same rectangular rod. The force is acting not on the center of mass. So what do you think will happen in this situation? The motion in this case for a non-hinged body is a combination of case 1 and case 2. So have a look. Look at the diagram. If the force is acting not on the center of mass and the body is not hinged, then the object is going to rotate as well as move ahead. So in this case, non-hinged body, linear motion as well as rotational effect, both are taking place. And these are the basics which you should know before starting this particular chapter of rotational motion. And now let me show you a video where you will see this subcase number 2 in effect. So a non-hinged body, the force is not acting on the center. It is going to move ahead, linear motion, as well as it is going to rotate. So have a look at this video. This is a video taken from the International Space Station. So this is an outer space where objects seem to float. So we have two objects here. These are actually CD players, and a person is going to push these objects. So let's watch this video. So when the push comes in, watch how the CD player is moving. It is not only rotating, but it is also moving ahead. And that is why this concept, when the body is not connected to anything, then if the force does not apply on the center of mass, then it is not only going to move ahead in a straight line, in addition to that, it is also going to rotate. And now we can start with the basics of this particular chapter. The first term is called the torque.